Hello, Kennedy. Hello, Connor. Hello, August. And of course, hello, Zane, and hello, Jared. So we are in, I believe we are in physical chemistry 364, 346, whatever. The goal is to model properties or understand properties of molecules and materials based on the wavy nature of electron, as a big goal to predict outcome of measurements in physical chemistry instruments. And right now we are focusing on the what? Particle in where?
Box.
Yeah, which models oligomers and nanostructures, right? We have already solved the time-independent Schrödinger equation, got energies, and kind of got wave functions. We didn't plot them, but we looked at them. So the main outcome of our previous meetings is that there are traffic signs. The electron inside the box cannot go with arbitrary speed and cannot have arbitrary energy. There are bands. And minimal energy is not zero, but something above zero. And this minimal 0-point energy depends on the size of the box. The smaller the box, the higher is 0-point energy, right? So if any of us needs to be hired as a high school teacher and we want to bring quanta and physical chemistry in there, we can finish the subject last time. So time-independent Schrödinger equation and solution for particle in the box. This is kind of minimal set, and then just mumble something about stars and lasers and done. But we are on the next stage and we want to get something more advanced and pleasant and interesting. So I remember myself throwing dough in the wall, not really, but as a verbal experiment. So what would happen if we want to see time progression? What if we prepare our electron not in one permitted state, not in second permitted state, but in superposition between them? So I already know the answer, so I'm not unbiased teller of the story, but it will model how it moves forth and back, and it will demonstrate whether it smashes completely into the wall or it starts reflecting a little earlier. So in some sense, we want to apply our knowledge and skills about time-dependent Schrödinger equation to this little problem. And as we go, I will torture myself and unfortunately you as well by offering one more additional methodology. So we already know time-dependent, time-independent, Heisenberg, and there will be so-called density matrix, which is sometimes much quicker and much efficient for time-dependent problems. But this is mathematical tool. Main goal is just to get physical chemistry insight on how it moves inside the box, and maybe try to project it to oligomers and nanostructures. Make sense? Okay. I think it is not 14, but 12. And here is not 21, but 19. Just so that you do not surprise if I send a reminder on Monday early morning and ask, like, did you submit? Yes?
So the homework one is just the part on the left. Everything that's
Yes.
typed, right?
Exactly.
And then the homework due on the 19th is everything on the right?
Correct. Yes.
Okay.
And how to say, homework 4 is kind of very much discount homework. So it is basically you visit tonight lab and write a lab report. And in some sense, I will already show how the outcome of this code should look like. So our class material is preparation for this homework. When I was a little younger and less experienced, I mumbled longer time. Now I have slides ready and I skip things. So maybe today we will be able to squeeze two logical lectures in one physical. So here is the space of ideas, not Cartesian space. And on x-axis we have methods, on y-axis we have systems, on z we have interaction with external perturbation, which we will at the very, very end of the class. So we do have two models, electron in free space and electron in the box. And we do have solutions of Schrödinger time independent Schrödinger equation. And today we want to solve time-dependent Schrödinger equation here. And instead of literally applying, I will invite everyone to do a little update, a little improvement, and so-called density matrix method that does have the same philosophy behind it, just a little bit different representation of things we do. So it's it seems very natural and very simple if you do these things again and again. But when you see something for the first time, there could be frustration of just one more object, one more word of terminology. So this is not complicated. Okay, and we have bigger arsenal. And as we progress through the course, we will have more systems, and at the end, we will look how they are. So what we have accomplished last time is that energies are proportional, ramping up as square of the integer number. They are inversely proportional to the size of the box. The smaller the box, the bigger the energies. First, zeroth energy and the offset. Then there is inertia, and there are fundamental constants. And the wave functions are just sine functions with different number of nodes, right? And there is a normalization that is designed to make absolute value square integratable of space given one, right? Normalization is needed not only for philosophically getting only one electron in the system, but also when we practice the bridge between abstract and real world, when we find so-called observables. If normalization is screwed up, then observables are also screwed up. So it is made not for pleasure of pure philosophy that we have the whole electron, not half of it, but to get correct observables. It's practical things. Zero inside, infinity outside. So equation for potential zero or infinity, depending on area of definition. Kinetic is second derivative, boundary conditions, and then we were solving it by plugging in general solution into boundary conditions and finding unknown coefficients. So due to old body Euler, we added together two exponentials and considered summation of trigonometric functions, and then solved equation for the C plus and C minus. We did found that C minus equals minus C plus, so these two cancel, and then we have two C plus, no C minus. And after playing all things together, we are getting this sine function. So coordinate here, size of the box in the denominator, so it cancels the dimensionality, and then phi is angle, n is natural number. So argument of sine is angle. if I would be mandated to make some quizzes, memorization of this equation is a good subject for quiz. And again, if any of us would need to teach at high school, maybe it's last two equations, energies and wave functions for the books are the only thing that are adequate for high school level. Other things that we come over here a little more advanced. So coordinate, angle, natural numbers, normalization. Okay, done with lecture 18, but please do not do that. So we all remember and know how to solve time-dependent Schrödinger equation. We take time-independent solutions, make each of them to accumulate phase according to the energy of this eigenstate, and then superposition of such solutions are constructed together with coefficients that match initial conditions, right? If we are trying to bring these abstract things closer to human perception, then we need to jump from wave function to distribution in space, to wave function squared, right? Because it is interpreted as probability density to find electrons somewhere. Wave function itself is a little crazy, and wave function squared is good. And when we do this trick, when we do this conversion from the wave function to probability distribution, then so each term in wave function is spatial part times time-dependent part. And when we take square of those, the resulting will be also summation of several terms, each of which has time-dependent part and space-dependent part. So we do want to simplify this procedure even before we start it. Just think ahead what can be simplified. And here is a little observation that we can project forward. No matter what happens with this electron in the box, no matter what are initial conditions, eigenstates are always the same. They're not changing. They do not depend on our vision or on our experiment, how we inject electron or how we photoexcite the system. So the spatial part in wave function and in probability distribution should be the same, independent on initial conditions. So we are finding it once and forever. So we may try to simplify something on this path. And initial conditions, we set them at time 0 and then we do not change them. They also like set once and forever. So I would try to combine these things and speed up the generation of the answer. So before we go to this big idea, here is a little thing, instruction, how to write a textbook on quantum theory, or how to do a front cover of a textbook of quantum theory. So if you look on the text, you see the figure. I'll better tell by words. So a lot of texts do show a figure which is quite abstract, although all components are correct. So one uses 2 dimensions, x as coordinate, y as wave function or wave function squared. And then if you plot several wave functions or several probability wave function squared, they would overlay over each other. And it would be a correct figure, but a little boring. So you have the wave function number 1 and wave function number 2, right? Sine with different number of nodes. If and the thing that I'm going to deliver next 30 seconds or next minute is not modern. It is from 1930s, where people just started coming over inertia of human thinking and bringing these abstract concepts. So if I want to graphically summarize both eigenstates and eigenvalues, so eigenstates, eigenfunctions already shown here, but we do not see eigenvalues. What if I do a crazy y-axis, which will combine both probability or amplitude of wave function plus energy? So the higher the energy of the state, the bigger will be offset on the y-axis. There is absolutely no science in this. It's only like low-level artistic work that is traditionally used in texts. But if you flip through pages, just want to give heads up so that you do not feel surprised, because some people do not care. Some people are happy with this idea, and some people telling it's not logical. We always are speaking that everything should be mathematically correct and logical, but what is on y-axis, oranges or apples? And here is the summation of them. So here is this picture that you will see in several books. X-axis is position, then y will be this wave functions, but they are offset in the y direction. And depending on the artistic taste of the author, some people show wave functions, some people show wave function squared. Right? And then tell about nodal points where it is 0 maximum, but it is wave function plus energy or probability distribution of energy. And some people really like to think on the language of these figures, especially if we are forgetting about real work, forgetting about implementations that just think that we have nothing except this box and electrons there. But then we are trying to model what would happen to this electron in the box if we irradiate it with light. So if this is analog of home, highest occupied, because it is only occupied, if this is analog of normal, lowest unoccupied, then optical excitation would promote electron from this one to this one. And then we can do this little graphical offset. So by going in energy so high, we are changing shape of the function from this one to this one. Make sense? Quite natural. But what we are going to do today will be slightly different. Instead of submitting the whole photon, which interacts completely and promotes it 100%, we will do probabilistic experiment where photon may have come, maybe not, or it was like a very weak photon that makes promotion of the ground state into excited only 50%. So since we are speaking about probabilities, it is very much allowed here. So we are going to look into state of the particle in the box where it is 50% in the ground and 50% in the excited. And if we do want to use Dirac notation, that I already forgotten who was presenting it, but it was in the past presentations. So if you use this angular brackets, then the initial wave function will be superposition of state 1 and state 2. And since if we want to keep normalization, one puts this normalization factor, which is you can either prove in class or set it up as an additional homework, or you can just do it. But basically, if you take absolute values square of it, 1 over square root square 1/2, 1 over square root square will be 1/2, 1/2 plus 1/2 is 1. So it is a good normalization. And let me quickly check online if I'm going to click or if there are any if there are any questions from Kennedy, Honor, and August. If there are no more questions, I assume that everyone is happy with the content, and let me go forward and continue. Okay. So in some texts, the stuff that we just did is written this way. So coefficient C1 squared plus coefficient C2 squared equals what? Or summation of C sub I absolute value squared equals what? Mod. Now this angular brackets will be just our wave functions, quantum states. First. So the question that we are setting up is to find probability that electron is located at a certain position at a certain time, which means predicting the future. And we already do have the protocol, the quantum cookbook, by matching, solving time-dependent Schrödinger equation by matching the general solution to initial condition. And I'm going to offer a little improvement to this methodology. So first, let's look on Schrödinger time-dependent Schrödinger equation solution. So we do have eigenstate, first and second. We do have normalization, and we do have accumulation of phase factors, right? Exponential minus energy of state 1 or e power times 2, energy of state 2. So basically, this is the solution of time-dependent Schrödinger equation. If we look for just to put sign that the assignment is done, formally, it is done. It doesn't help us to analyze any chemistry or physics behind it, but formally, it is a solution. If we need an analysis, we may do two things. We don't know. At time 0, we had coefficient C1, C2. If time is bigger than 0, we can insert this time factor inside the exponential coefficient. Tell the exponential coefficients are time dependent, right? Since absolute value of imaginary exponential is 1, the normalization will be not correct. It will be only change of the relative change of phases. Okay. Now, if we need to go into real world or just to analyze what we have done, one can do two things. First, find probability distribution by making absolute value square of this solution, and find expectation value of something of interest, observable of interest. And the simplest one is position of coordinate, position of product. So before on the way to these goals, I'm going to do a little experiment. So composing the product of wave functions, which will be not the scalar product, but direct product. That also we were going over in both in postulates and in MATLAB stuff. Right? The thing that converts vector into a matrix. So if I am going over this experiment, if I'm taking this psi cat times psi bra, each of them is a summation of two terms. The cat doesn't have conjugation, bra does have both conjugation of the various functions and conjugation of the expansion coefficients. Since they are time dependent, it will mean that they will go backwards in time, right? We flip sign in front of that imaginary thing. And if I like to practice a little algebra, I can open the brackets. Sure, when you need to relax, you start opening brackets. That's a fun. So 2 times 2 will be 4, right? First term in the first bracket times first term in second bracket. Cat, bra. Expansion coefficient without conjugation, expansion coefficient with conjugation. Make sense? And if we continue to do the same, it will be first, second, second, first, second, second. But they are all inverted. First cat, then bra. And here non-conjugated, conjugated, non-conjugated, conjugated. 1, 2, 2, 1, 2, 2. Okay. So the explicit values for this products of expansion coefficients is our tool on the way to do two things: to plot probability distribution in space and to find expectation values. And right now, when we do this oversimplified problems, it doesn't matter which method to use, but if one wants to describe more complicated and advanced systems with time-dependent aspects, this thing where we are going to would give immediate benefits. So right now, I do count on your temporarily trust to me. Like, I'm not showing derivations, and unlike previous lectures, I haven't shown the final answer. So you are like, if you play computer games, you are coming through the fog of war where you do not see the next step. But the answer will be probability distribution reflecting electrons smashing into one wall and then to another one. So on this way, we do have this time-dependent coefficients. Each of them is imaginary exponential. When we do have number here and number one here, number one there, conjugation means flip of the sign, and multiplication of exponentials with opposite, imaginary exponentials with opposite signs is like e to the power x times e to the power minus x. Once again, e to the power x times e to the power minus x. You can write it down.
You just add x minus x, then e to the x minus x.
Which
equals
e to the power 0,
which is 1.
Super. Yeah, I'm happy. Thank you. So, anytime we have one here and one there, it will be just 1. So time dependence disappears. 2 and 2, time dependence disappears. And here we will have subtraction of energies, a little more complicated, but if you can simplify something, it's already a good deal. So if we take this object, and I didn't introduce, I wasn't polite. If polite people introduce new person to the community, you need to give them a name. So this cat times bra has a name. Its name is density matrix. Density matrix. And if one performs so-called trace, then it will be just product of wave functions. So from the density matrix, one can go immediately to probability distribution. So why there is a word density? Because product, wave functions product gives, on one interpretation gives probability distribution, on another interpretation gives density. So there is more out in this area of space, less in that. And matrix, because there is an object with two indices, and sometimes it is written as a matrix, as we will see later. But now we are coming to exploration of probability distribution. We have this basically the same stuff, and we can plug in explicit expressions for the wave functions and do substantial simplification of this pairs of expansion coefficients. So 4 terms. Each term is a product of 2 factors, time factor and space factor. So the space factor can be called element of density matrix. Space factor is just product of eigenstates. If you multiply, then instead of square root of L, it will be L. So this is Greek letter rho, which is typically used for density, right? Rho 1, rho 1, 2, rho 2, 1, rho 2. And here we have products of the wave functions. This one will be like a camel with a single hump. This one will be like a camel with 2 humps. And those will be a thing that goes below the x-axis and make negative things. Now the elements 1, 1, 1, 2, 1, 2, 2. 1, 1, the energy, the accumulation of phase forward in time and backwards in time compensate each other. And we have 1/2 because it is probability that system is in the ground state. So density matrix element 1, 1 is 1/2. The element that corresponds to excited state, we have 1/2 because of the initial condition, and then propagation forwards in time and backwards in time compensate each other, so you will have 1/2 time independent. For the so-called off-diagonal elements, because we can write this 4 numbers in a matrix, this 2 will go on the diagonal, this off-diagonal. Then we will have subtraction of energies of the states, forward and backward order. Make sense? So we are approaching the answer. So here are the spatial dependencies and the images that we just discussed. So camel with 1 hump, camel with 2 humps, and this stuff. And then the camel with 1 hump and camel with 2 humps their relative contributions to the answer are not changing. They're constant. We just add them together. But the contribution from this stuff that goes up and down has different relative contributions over time. So we have one of them is contributed by exponential moving forward in time with a certain pace, another going backwards in time is a certain pace. And then we need to add them together. No? Maybe I skipped. So if we have this stuff and this stuff, one comes with E minus I delta E T H bar. This one comes E plus I delta E T H bar. They look the same, right? Two here, two there, one here, one there. And so, which means we can put this spatial part out of brackets, phi 1, phi 2, and inside brackets we will have E I delta E time over H bar plus E minus I delta E T over H bar. So when we add together two exponentials moving on the opposite direction, what does old body Euler tells us about it? Yeah, absolutely correct, but can you verbalize it in from artistic way to like nail it down to the word of words?
Constructive way?
Yes, but more mathematically definitive. So each exponential is summation of cosine plus I sine. Here, if we have minus, it will be cosine minus I sine. So I sine here and I sine there will cancel, and we will get two cosines. So it will be real, right? Okay. So here is our original plan. I probably was nervous and tried to rush forward, but here is this stuff. So forward in time, backwards in time, it will be two cosines, energy different over H bar times T. And the stuff that we placed out of brackets is this thing that goes up and down in space. So this will be the only thing that changes in time. So we need to add together two camels and this time-dependent part. And then their summation needs to be evaluated at each point of time, and it will be answered how our distribution of density or probability to find an electron will evolve over time in space. So the plan is that we will do it by pen and paper when we meet on Friday. We will do it by computer today during the lab. And here, how it will look. So basically, it's the answer of the Monday homework due on Monday. It is what is going to come out of our practice tonight. So it starts where there is a superposition of one hump and two humps, but because there is a term that changes phase, cosine gets positive and negative, it shows that relative contribution of left and right changes, right? So this is an electron encaged in the box. And in the superpositional states, it corresponds to this electron moving forwards and backwards. But since it is not classical continuous motion, it has several features. So in average, yes, it goes forwards and backwards. But it never, the probability near the wall never exceeds zero. So it stays zero. These boundary conditions are always kept correct. You just approach it as much as it can, and then it goes back. So this is what would happen to like tennis ball if our classroom becomes smaller and smaller, and I would become a quantum dwarf. So it will not approach the walls completely. It will reflect back in a special way. Done? Done? Any questions are welcome either in class or from the line. Kennedy, Connor, August, feel free to type or ask a question. And if there are no questions, you are welcome to disconnect now, and I look forward to see you guys 5 p.m. QBB 132.
Sorry. Okay.